Okay, so I think this is where we left off in the last sessions. We look at the discussion on the differences or why we can't get the von Karman shape or a characteristic on our simulation. Okay, remember in the lab, we perform in the second lab, we perform a simulation where we observe the flow passing through an object. And basically the discussion that we had last time, why we didn't see this characteristic, the behavior, the wake behavior behind the object as observed by the von Karman vortex. Okay, so the reason is because for the ANSYS that we use, the software that we use for our lab, it uses the RANS method. Okay, RANS refers to Reynolds average Navier-Stokes, which we are going to discuss later. Okay, why RANS can produce this type of shape or characteristic as observed by this von Karman vortex. Okay, I think it's quite interesting to see some quotes here. So you can see here the first one from Heisenberg, a German Nobel Prize in Physics in 1932. So he said, when I meet God, I'm going to ask him two questions. Why relativity? And the second one, why turbulence? I really believe he will have an answer for the first. And similarly, from Sir Horace Lamb, a British, so he said, I am an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other one is the turbulent motion of fluids. And about the former, I am rather optimistic. Okay, so you can see here two very well-known scientists basically highlighted the issues of the difficulty of turbulence. Okay, there are no right answer or no right explanation to the turbulence behavior up until now. Okay, we just try to understand, and we still have so much to study about turbulence. Okay, so that's why this lecture is intended to give you some perspective. Okay, what is turbulence? It's rather easy when you have some choices in ANSYS, for example. When you want to conduct a simulation, you can just go to one of the options that you have, and then you can click option 1, 2, or 3, K epsilon, K omega, SST, RNG, and so on. Okay, but what does or what the choices, what does it represent? Okay, what does it mean to choose one option than the other? Okay, so what does K epsilon, what does K omega refers to? So I think that's the issues that we try to explore here. Okay, we are not going to go into detail in terms of the equations or the meaning of each equations that is provided or that is available in ANSYS, but we are going to discuss the turbulence in general. Okay, what is turbulence? Why is it difficult to understand? And some of the difference method that can be used to simulate or to replicate the behavior of the turbulence in a model. Okay, so that's what we're going to do here. All right. So for the characteristic of turbulence, there are several terms that I think is quite important that we should understand. Okay, first one, we need to understand about the turbulence. It is random, meaning that you cannot predict the behavior of the turbulence. Okay, so it is disorder and no repeatability. Okay, it has no set or repeating pattern. Okay, so it is random. Secondly, it is vortical, which is very high in concentration and intensity. Okay, what is vortical or vorticity? Vortical or vorticity is basically the swirling shape, okay, or the swirling movement. Okay, so these are the vortices. Okay, it can be big, it can be both small. So if you notice, when we first start this lecture, we look at this example here. So you can see over here, once the flow passes through an object, okay, the mixing that is happening here, it is in terms of vorticity, in terms of the shape of the turbulence will be in terms of the swirling movement. So that's vortex or vorticity, okay, the swirling movement. Okay. Okay, it is also non-linear and it can be in 3 dimensions. So just imagine right now, again, we cannot expect it to be linear, meaning that we have, let's say, position 1 and this is position 2. We cannot expect the path of the flow from position 1 to 2 to be a straight line. So it is highly non-linear. And then when we're dealing with the flow, you need to remember we are not just dealing with a 2D problem. It is a 3D problem. Okay, so meaning that we understand that if we look uh, from the front view, okay, remember when we did our labs 1 and 2, we created a domain for our problem, and the domain, okay, from the front looks something like this. Okay, so meaning that from the front view we have, let's say this is our x, y, z. So we have x, this is y, this is z. Okay, so from here, we can see that we have y, over here y, and this is x. That's 2D. Okay, but you need to remember, if we look in great detail, what we can do is basically the water column or the depth. Okay, we call it water column. The water column can further be divided into several slices or several layers. Okay, and each layer here will have a different movement, or the vorticity, the swirling movement, it can be in terms of x, y, and z. Okay, so it is highly non-linear, and it is in dimensional. It's not just 2D. Okay, so it's in terms of x, y, and z. So it's very complicated. Then for point number 4, the continuity of any structure, vortices are strong structures. Okay, it's called a structure or characteristic. So reflected in a continuous spectrum of a fluctuation of a range of frequency. So it fluctuates. It's not just a specific set. Again, it's not something that you can establish as, okay, this will be as a certain wavelength. No, it is random and it is fluctuate, meaning that it can be big, it can be small, and it can be alternate. Okay, it is not just big and then suddenly small and then big again. No. So there's a set of structure that we need to understand. And then when we talk about turbulence, it also involves energy cascade. Okay, energy cascade, which is what we're going to talk in a bit, meaning that diffusion from large energy into a smaller energy. So that's energy cascade we're going to discuss in a bit. It's about irreversibility. I think it goes back to like thermodynamics too, if you remember. There are things that once it's done, you can't revert back to the original position. Okay, and dissipativeness. Dissipative means the loss of energy. So these are the things that we're going to discuss about turbulence. Okay. And then about intermittency, point number 6. Turbulence can occupy only parts of the flow domains. Okay. This can relate to, again, if I can go back to our first slide here. All right, so if you notice on here, the figure on the left, if you notice the turbulence region, so if I can just color them, let's use another color, black. Okay. I'm not sure you can see this. Okay. The turbulence region behind the object, basically, there is a certain distance to it, meaning that the turbulence will not propagate or will not be basically maintained over a long period. Okay, so this is what we want to discuss. There will be energy cascades, will be energy dissipation, meaning that the flow, okay, after it passes through the turbulence stage, it will recover to its original velocity. So meaning that if we have, let's say, this is 1 meter per second before the object, and then after a certain distance, you will get again 1 meter per second. Okay, so this is about intimacy, meaning that the turbulence is only uh, uh, happens at a certain region or a certain location, and then after a while it will pass through that stage. Okay, so just 1 second. All right, so over here, so for my work, for example, okay, if we are looking from the side view, this is side view. Okay, this is our domain, and let's say we have our object over here. It's similar to what you did for your second lab. Okay, let's say this is the inflow velocity, 1 meter per second. Okay, and then in the immediate region downstream, meaning behind the device, okay, let's say from here to here, we call this region as near wake. Okay, near wake, and the distance, okay, how you characterize near wake, okay, how you define near wake is usually from literature is between 3D to 5D. D here, again, if you remember from the lab, refers to the diameter of the object. Okay, so if our object is, let's say, 1 meter, then our distance will be between 3 meter to 5 meter. That is categorized as the near wake. So the near wake is where you will have the highest fluctuation or turbulence. Okay, and then after this region, what will happen is, okay, you will have some of the turbulence will still persist. You will still have the characteristic of the turbulence. The mixing is still happening. So this, after the near wake, this is what we call as the far wake region. So far wake region is usually defined, of course, 5D and above. Okay. Okay. For my case, for example, when I did my research, I was interested to find out how far does it take for the wake to recover. So the wake here refers to basically if this is our object, okay, the turbulence, basically the mixing behind the device or the obstacle. Okay, so I was interested into to find a far wake. Okay, the far wake usually will persist up until it can be from 11D, 15D, or even 20D. Okay, it can be meters, it can be kilometers. Okay, so this is the far wake, basically 5D and above. 5D and above. All right. So after the far wake region, okay, at one point, okay, at a certain distance, let's say assuming, okay, after, let's say, let's put some value, maybe after 15 diameter, 15 multiplied by the diameter, then the wake will recover. Okay, what does it mean is, okay, from 1 meter per second, then it will become again 1 meter per second after the mixing, after the turbulence. Okay, so the question is, what is happening in between that? So meaning that what is happening, if you look clearly, in this region between the near wake and far wake. Okay, when the mixing happens, what is happening is there will be a deceleration of the flow. Okay, and if you notice from your second lab, from the flow contour, okay, you will observe basically, let's say if you have 1 meter per second, you will observe velocity deficit, okay, deceleration of the deficit of the velocity. So maybe behind the object, you'll get immediately in the near wake, the velocity might be, might be, let's say 0.5 meter per second. But as it goes further than the device or the object, it will start to recover. So it will be 0.5 and then 0.6 here, maybe 0.8, and then it will recover to 1 meter per second. Okay, so the reduction in velocity, that's due to the turbulence. Okay, the turbulence, the mixing of the turbulence causes the velocity to lose some speed, okay, which we are going to discuss basically due to the energy cascade, okay, from large energy to a smaller energy, and because of the dissipation as well, okay, how the energy loses the energy, the entities or the turbulence loses the energy in terms of from kinetic, okay, because of the movement of the water from the kinetic energy into heat, because of this dissipation into heat, right? Okay. All right. So let's learn about the um, hypothesis. Hypothesis means some proposal, okay, made by scientists, okay, how they, when they try to understand turbulence, how they can explain the behavior of the turbulence. The first one is from Richardson, an English scientist. So he proposed that the turbulent cascade for energy in 1920. Just 1 second. Okay. So energy at cascade. What does cascade mean? Or the cascade means a fall down, okay, from a higher region to a lower region, or from something large to a smaller scale. So what he's trying to explain is that the energy is transferred from large scale of motion. So if you noted over here, this is large scale motion, and what it meant by motion, if you look over here, this is the direction of the swirling, the vorticity basically. The turbulence always behave in the swirling motion. Okay, so it basically he proposed that the energy is being transferred from a large scale of motion to the small scale, meaning that it started from a big a chunk of motion, and then it gets smaller and smaller. So it gets smaller by the direction of the arrow. Okay, so that's what his proposal is. Okay, and the dynamics of such system is non-linear, meaning that the direction and the size will not be constant. For example, what he proposed over here, if you can see from the figure, this is a simplification of the explanation. But in reality, it will never be the same size. For example, over here on the large scale, is the drawing shows symmetrical or same size or likewise size of the scale or the motion. But in reality, if you look over here, okay, the scale, the shape, the rotation, the vorticity of the motion, they are all non-linear. It will not be the same. It is largely independent. Okay, so you can have a mix of large, small, medium scale, and very small scale motion mixed into one movement. Okay, and then the energy cascade. Okay, basically how to explain it in detail. I think the scientist here, Kolmogorov. So this is again, if you notice, this is the simplest example that I've been I've been discussing this with everyone from the first day of the class. It's all about a simple object. It doesn't matter the shape of the object. It can be cylinder, it can be this, it can be rectangle. It doesn't matter the shape of the object. But the characteristic or the expected behavior or motion will be the same. Okay, so we have a mean flow, so meaning that we have u free stream. Okay, and then after it passes through the object, okay, this is what we have been talking about. So there will be mixing of the fluid or the flow, okay, behind the object. Okay, so this is front, and this is basically downstream of the object. Okay, and you can see here the mixing. Okay, it will be in terms of mixing between large scale motion, medium scale motion, and a very, very small motion. Okay, and it is a mix of everything. Okay, and the transfer of energy, Kolmogorov he proposed, looks something like this. It will be from large to small. Okay, and he went one step further to basically discuss in terms of the he explained the transfer from large to small. He breaks it into three characteristics. First, in terms of production, meaning that that's where the turbulence is the highest. Okay, energy is being created. Okay, because remember, it was at first a very calm surface, for example. Okay, and then it was laminar. Let's say laminar, and then suddenly after the object passes through the obstacle, after the flow passing through the obstacle, there is a mix of everything. So that's where production of energy happens, okay, or the production of turbulence happens. So that's the first stage. Then from production, it goes into transition. Okay, transition meaning that it goes from highly turbulence into a transfer of energy, or the transition between large into a smaller scale energy. Okay, and the last one is disruption. Disruption basically energy dissipation. Okay, so from large, okay, if you see here, this is large energy. Then finally, at the end, we have a small energy. So he described it as a disruption. Okay, so the question is, where does the energy went to or goes into? Okay, from large to small. So remember, when we learned about thermodynamics, energy can change form from one form to another, but it cannot be destroyed or created. So meaning that the large scale motion or the large energy during the production part on the left, okay, it needs to be converted into some kind of other form. Okay, so the disruption here, basically, after the large form motion or the large energy, now is being transferred or is being dissipated into heat, hence losing the energy, then hence is described as destruction. Okay, so that's how he categorized it. Started from production, which is the highest energy, then transfer, meaning that transition between large scale into a smaller scale, and finally the destruction, which is due to the dissipation of the energy into heat. Okay. And then another hypothesis from Sir Taylor, he hypothesized on the frozen turbulence. Okay, as the mean flow V advex the eddies, the fundamental properties of the eddies remain unchanged or frozen, since the turbulence fluctuation V prime are much smaller than the mean. Okay, so the V here is the mean the mean flow, okay, the mean velocity. So because he theorized that because of the fluctuation, the velocity fluctuation is smaller than the mean. Okay, so he make an assumptions that the eddies or the turbulence, okay, can basically be assumed to be frozen or maintained, okay, at a certain distance. So you can see from this diagram. So the eddy before passing through the wind turbine, okay, let's say this is the eddy size. Let's change color. Okay, the eddy size here. So the eddy size before the turbine is just the same as the eddy size after it passes through the turbine. So that's what he proposes. Okay, the Taylor microscale responds approximately to the initial subrange of the energy spectrum. In such range, the energy is transferred down from the largest scale to the smallest one without dissipation. Okay, so in this case, it's quite different from what we had before, meaning that before someone theorized that the energy cascaded, okay, from large scale energy to a smaller scale energy. But now he proposed that the energy basically passes through without dissipation. It maintains the range, okay, before and after. So this is from Taylor. Okay. Then from Kolmogorov, he's a Russian. So he said in every turbulent flow at sufficiently high Reynolds number, the statistic of the small scale motions have a universal form that is uniquely determined. Large scale L vortices are anisotropic. Okay. So if you draw again our diagram, okay, let's say this is our large scale motion, and then it's getting smaller and smaller here, and then finally very small motion. Okay, so the last scale, okay, which basically here on the left, they are anisotropic. Okay, if you remember anisotropic, it means dependent on the direction. Okay, so next one, for small scale vortices lose all structure information about how they were created. They become homogeneous and isotropic. Isotropic here means they are the same in all direction, okay, or similar. And at the small length scale, the energy input and dissipation are in exact balance. Okay, so meaning that when we are dealing with the small scale, okay, at the end here, okay, what he said basically the energy input and dissipation are in exact balance. Okay, they are basically the energy is being transferred or is being changed from the large scale, okay, into a smaller scale due to the heat dissipation. Okay, and if you notice all this discussion we had about turbulence, mostly they involve assuming we are dealing with a very large Reynolds number. Okay, when we are dealing with highly turbulence region, because the name itself turbulence modeling or turbulence problem. So this problem will not exist for lamina because lamina is a very smooth flow. You don't have all this mixing. Okay, so when we are talking about turbulence, we always assume we are dealing with a very high or large Reynolds number. Okay, so we talk about this from production to transfer to the destruction. Okay, so the we're not going to details into the equations of the turbulence. Okay, but if we want to understand a bit better, when we look at the Kolmogorov scale, okay, what he proposed is this plot from production to destruction. Okay. At the large scale, you have the velocity u, and we have the L. L here refers to the length or the size of the turbulence or the vorticity. Okay, and then as we go on until the smaller scale here, okay, so energy is being dissipated, meaning that it transfers from highly kinetic energy into a less kinetic energy region due to dissipation of energy. So kinetic energy is being transformed into heat energy. Okay, right. So covered about this. Okay, what do we know for sure? Okay, this is interesting. If you notice, most of the hypotheses or the turbulence concept that we covered or we look or that we use up until now, most of them are based on the assumptions formulated in the early 30s or 40s. So what, 80 years now? Okay, so these hypotheses are made on the basis of logic and dimensional analysis of the flow. Okay, and yet we also look for the rigorous or mathematical proof. So meaning that most of them, okay, they propose the hypothesis based on either experimental or analytical calculations, okay, but they also basically based on logic, okay. And then, of course, in many cases, there is extensive experimental evidence that they are correct. So meaning that what has been proposed 70, 80 years ago are still being used up until today, meaning that no one is disputing what they have proposed. Okay, so the problems that we look again, if you remember about the golf ball, the dimples, okay, that has been proposed long ago, and yet up until today, that observation still stand until today lah. Okay, it doesn't change. Okay, so that's a bit about turbulence. Okay, now let's move a bit into the modeling part. Okay, the reason why we need to model turbulence. All right, so we can numerically simulate inviscid. Okay, if you remember, inviscid refers to the Euler equations or laminar flows using directly the governing equations that we derived. However, despite the performance of supercomputers, turbulent flow represents a significant problem. Okay, why? The first point, the direct simulation of the governing NS Navier-Stokes equations, okay, called DNS, direct simulation. Okay, DNS here stands for direct numerical simulation. Okay, so this is direct numerical simulation. Okay, so we can use the first method. This is the first method, DNS. It is only possible for simple case or cases that use low Reynolds number. Okay, I will explain later. Okay, what does it mean by DNS? Okay, so it can be shown that the number of mesh point scales, okay, as shown here, Reynolds 9/4, while realistic applications have a Reynolds number 10 to the power of 6 or 10 to the power of 9, meaning that in the normal applications, we are dealing with a very highly turbulence region. Okay, we are not dealing with something that is very low Reynolds number. In most applications in daily life, car aerodynamics, jets, spaceship, we are all dealing with a highly turbulence region. Okay, so because DNS is basically direct numerical simulation can be reserved for the simple and low Reynolds number, is not really suitable for what most of the researchers are trying to do. Okay, I'll explain later what DNS, LES, and RAS comparison. Okay, so it says here DNS is still very useful as a research tool, but the majority of the cases we need to apply some model of turbulence. Okay, so let's have a look. Okay, so now into detail, what is DNS? Okay, when we are using DNS approach or DNS method, we are not modeling the turbulence, meaning that we are solving the turbulence characteristic as it happens. Okay, so no turbulence model at all. Okay, we are not modeling, we are not simulating the turbulence. We are solving the turbulence that is happening in the problem or in the project or in the issues that we have. Okay, so it's regarded as an analytic solution to the Navier-Stokes equation. So it solves all scales of motion. So you previously we look at the Kolmogorov scale. We have large scale motion, and then small scale motion. So when we are using this approach, DNS, we are basically solving all the scales from the large motion up until the small motion here. Okay, so we are not modeling anything. But the drawback is it is extremely costly, and the cost here refers to the computational cost. Okay, and only used for scientific purposes. For example, validate turbulence model, fundamental understanding of the model, and more importantly, it is limited to very simple cases. Okay, you highly unlikely to find research that use DNS to solve, for example, car aerodynamics, or even, for example, aerodynamics of a jet. Okay, you're very highly likely to see that. Okay, because it is extremely costly when talking about computational cost. Okay, right now, okay, even though there are a few cases where we need to use DNS, okay, it is only possible because we have advancement in technology due to computers advancement. Okay, in regards to this point, okay, if you watch this movie Hidden Figures, okay, I've watched this I think a couple of times. It's a very good movie. It's about engineering. It's about a group of people at NASA where they try to find solution to send US astronauts to the orbit, not to the moon, to the orbit, where they have to solve set of equations manually, meaning that they have to use analytical equations. That was in 1960s. So in the movie, right, I think just before 1970s, they purchased IBM. NASA just purchased IBM machine, IBM computer basically, to help them solve some of the complex problem. Okay, solve and also validate. Basically, humans they make analytical calculations, and then the computer will try to verify the calculations. Okay, but at that time, the computers, okay, it's not like today. Let's not talk about the 70s or 80s, okay? In 2004, let's say early 2000, you would be lucky to find a pen drive with 128 megabyte of storage. Okay, I'm talking about 128 megabytes for this is not RAM, storage for pen drive. Okay, because when I was a student, okay, if roughly about in 2004, if I can get 512 megabytes of pen drive, then I will be lucky because it's expensive, very, very expensive. But compared to now, okay, now is 2021, in the early 2000s, 2020, 2010, I think you can get, now easily you can get 64 GB pen drive just off the shelf. Okay, so it just shows the advancements of technology, computer advancements has basically progressed rapidly from the 70s, 80s until now, 2021. Okay, so we are only possible to use DNS method right now, okay, because we have advancement in the computer technology. Okay, we now have supercomputer where we have like units in teraflop. It's like 10 to the power of what? 12, if I'm not mistaken. The RAM and the speed is just insane. But still, DNS is not the go-to solutions for most problems. Okay, because it is just extremely costly in terms of computational resources. Okay, so the next one, aside from DNS, is what we have LES. Okay, all right. Just give me 1 second. Okay, so the second approach that we can use to model turbulence in simulation is a method that is called LES, a large eddy simulation. Okay. So for this one, it solves directly the filtered Navier-Stokes equations. Basically, it solves the large scale vortex structures while filter the smaller subgrid resolution scale, meaning that it can basically resolve most of the resolution or the size of the vortex, okay, the structure. They call it vortex structure. Okay, it can solve most of the structures. Okay, so in DNS previously, it can solve all the structures. It can solve all the vortexes. Okay, but for LES, it can solve most of the structures, not all. Okay, and it uses a model for turbulence to dissipate the energy. Okay, at the subgrid scale. Okay, at the very, very small grid scale, still some sort of modeling is needed. Okay, for a very, very small scale. This is a clear trend in engineering since the last decades, and it allows for, excuse me, and allows for more complex cases. Okay, and in terms of computational cost, it is medium or intermediate, which is basically weeks of runs. Okay, I will explain in a bit. Okay, the differences between the LES, DNS, and also runs in terms of the running time. Okay, so far we understand that for LES, it can solve most of the structures. Okay, it can solve most of the structures. Okay, and the smaller one, it uses a subgrid resolution where some sort of the modeling, turbulence modeling, is still needed. Okay, so you can see here, model of turbulence is still needed. Okay, to solve for a very, very small vortex structure. Okay, this is the trend nowadays, LES. And then in terms of the cost, okay, is less than what we had for DNS. Okay, the last one, the third approach is what is we call it as RANS, Reynolds Average Navier-Stokes. This method basically use the decomposition of variables into two main variables. Okay, so when we're dealing with u, for example, okay, in this case they use v, let's say v, the velocity, okay, in y direction. The v is now basically, instead of just v, solving for the right value of v, it consists of two decomposition or two values. It is the mean, okay, v bar, plus the v prime. Prime here refers to the fluctuation. Okay, so mean means it takes the mean value of the velocity in this direction, y, and then it takes the fluctuation, the difference between the real value and the right value. Okay, the fluctuation, sorry, the value at that point, okay, against the mean value. Okay, so that's how they get the fluctuation. Then a time averaging is operated, and we have two additional terms. Okay, okay, in the Navier-Stokes equations. Okay, more importantly in this part, so the dissipation due to turbulence is entirely modeled. So meaning that starting from the large vortexes into the smallest vortexes, all of them are being modeled. Instead of being solved, they are all being modeled. And the good thing about runs, okay, as you probably understood by now, okay, from your first lab and second labs, it is very, very affordable in terms of computational cost. Okay, we can use considerably coarser grids, okay, compared to LES. Okay, remember, even when we have a very, very powerful computer, okay, but if we are not using the correct grid size or the mesh elements, then the output of the simulation is just useless. So it has to be based on the methods that we use. So for runs, for example, you may use a grid that is slightly coarser compared to LES. Okay, okay. So right now, the runs method is very, very popular because of the good in terms of the computational cost, very, very low. Okay, and it is used for most of the commercial and or open source packages. Okay, and we have so many models available. As I said at the start of this lecture, we have K omega, we have K epsilon, SST, RNG. Okay, but we need to understand the pro and cons of each models before we can use them. Okay, we are not going to discuss that in this course, but just to understand, for runs, everything is being modeled. Okay, but of course, when we discuss about the output, okay, we need to understand when can we use runs, when the result of runs is acceptable, what can be simulated using runs. We have to understand that it's not just okay, runs uses less computational resources, then let's go for runs. Okay, so it depends on the problem. It's always depending on the problems in choosing the right methods. Okay, all right. Okay, so if you can see here again, if we go back to the Kolmogorov plots, if you remember, this is largest energy scale, largest vortexes, okay, and then this is transition in the middle, and then we have the smallest one on the right side. Okay, so if you look from this simple diagram, okay, if you use runs, okay, this one, it can solve the largest scale or the largest vortex structure, okay, meaning that this part. So that's runs. Now, when we go to LES, okay, sorry, for runs, okay. So the rest, from medium until smallest, all the models, all the structures are being modeled. So meaning that the turbulence model will help the simulation to replicate the behavior of the flow. Okay, it's being modeled, not being solved, it's being modeled. Now, for LES, it can solve most of the range of the sizes of the structure. Okay, up roughly, roughly up until here. So if we just can color this, so this is roughly the region where LES is significant, meaning it can solve most of the range, okay, except for the very, very small one on the right side. There, at the subgrid resolution, some sort of model needs to be introduced to solve the small scale. The rest, for DNS, it can solve all structures. Okay, so that's DNS. Okay, but remember, it comes with the drawback where you can only use it for very simple problem, and usually right now when we are dealing with real applications, it's almost impossible to use DNS because it consumes too much time. Okay, and you cannot solve in detail. Basically, it's solved in detail. Of course, DNS can be used to solve detailed problem, but if you want to solve what is happening, for example, at fighter jet, for example, the aerodynamics of fighter jets, then it will take forever to solve each individual turbulence or the vortexes that is happening for the aerodynamics part. Okay, all right. So here are some simple examples to show you or to give you some perspective, okay, the difference between DNS and LES. Okay, so the LES, it captures the large scales but misses some details. Okay, the keyword here is this, some details, just a very small details. So you can see here DNS and LES. So DNS, it can solve all the vortexes, all the turbulence that is happening, all the mixing that is happening. But LES, okay, even though you can see the shape, okay, of the turbulence, but it's not full, it's missing some of the structures. Okay, so this is in 3D, example in 3D. Okay, as I mentioned previously, when we're dealing with turbulence, it's not just 2D, we are dealing with both X, Y, and Z. Okay, so this is a very good example just to show you DNS and LES. Okay, how about LES and runs? Okay, if you notice in your lab 2 report, okay, when the flow passes through the object, roughly this is what you see, roughly. Okay, even for your lab 1, the flow just in a simple channel. Okay, but what is happening really should look something like this. Okay, so the comparison between runs and LES. Okay, there is some mixing between higher velocity region and the lower velocity region. Okay, if you look into details, okay, if the structures are being resolved or being simulated properly. Okay, but for runs, because it takes the average value, so that's why you see everything over here is red, everything over here is yellow, because it takes the average value. So if you see over here, that's the average value, is yellow. Okay, now the average value from here to here, that's red. Okay, so that's how runs works. Okay, all right. So to give you a better perspective, I think let's watch some videos of the simulations that has been done by one of my colleague at the University of Edinburgh when I was a student in my study there. Okay, just give me 1 second. So let's stop. Okay, this is a simulation, of course. Okay, so let's have a look at. Tinjauan di. Oops. Okay, so it doesn't have a sound. Okay, so this is simulation basically between this is for Isle of Islay. Basically, Isle in Scottish basically is just terusan, it's like a selat, like a strait. Okay, Isle of Islay. So he's trying to. This is done by Dr. Angus Critch. He is one of the researchers at University of Edinburgh. So he's trying to simulate the hydrodynamics that is happening in between these straits at this particular location, because this location has been identified as a potential location to deploy tidal turbines. Okay, so before the company can just invest or put the tidal turbines straight away, we need to understand, okay, first the right locations where we can put the turbines, okay, and then the directions, and then how many turbines, the optimal turbines, and then the arrangement. So there are a lot of consideration. So before we can do all that, it is better for us to get some understanding of what is happening by simulation. Okay, so this is done by using LAS, okay, large eddy simulations method, using a software that is called Fluidity. Okay, so I'm going to play the video now. Okay, so this is basically a simulation that shows what is happening. Okay, at a certain location and also at a certain period time. So these researchers, they need to put to have the correct input at the boundary. Okay, the data of the tidal, what is happening at this particular time, how many tidal constituents basically are observed. So you can see here, we can see all the vortex shadings. See, the flow is going to the right and then suddenly going to the left. That's because of the tide, the change of tide. Okay, uh, the rise and ebb of the tide. Okay, you can see that the flow first is going to the left and then suddenly it's going to change direction because the tide changes. Now it's going to the right. Okay, so then we have a 3D cut away showing the velocity. So what is happening underneath the water? Okay, the velocity at the water column. Okay, so that's where the potential location to deploy the turbine. Okay, so you can see at the red, the velocity is about maybe 2.8, 2.6. So it's very, very quick moving flow. So non-hydrostatic. So meaning that it is the calculation, the flow is being calculated in terms of the X, Y, and Z. Okay. So now they are showing the back stress with surface vorticity. What does it mean is, instead of just looking at the topography of the islands, now we also need to consider what is the shape of the bottom of the location, okay? At the bottom of the location. Okay, so that's one video. I've got a couple more. Okay, just 1 second. Okay, so we have okay. Again, this is from the same researcher, Dr. Angus Critch. This is for a different location. So Canadian tidal straits. So you can see that, okay, after the flow passing through the islands, what is happening? You have the vortex shading at the back. You can see that the mixing over here, the vorticity. And remember, this is a real location. Just imagine this is, let's say the mixing happens up until, just 1 second, just let's have a look again. The mixing happens maybe a few hundreds meters or even maybe kilometers after the island. Okay, so that's important because we need to understand where to put the device, for example, in this case, tidal turbine. Okay, so this is the behavior that we are observing. Okay, all right. Okay, see all the vortex mixing over here at the back. Okay, and the flow coming from the right and left. Okay, and where they met, and then how it propagates until the end. Okay, remember, all this simulation is useless unless we put the correct boundary for our work, unless we are using the correct topography, meaning that these islands, the geography, the coastline is being extracted correctly from the source. So your simulation, for example, his simulation basically depends on several factors, not just It's not just about simulation. It's not just about putting some value and getting the output. It depends on several factors which have all which definitely have influence on the output of his simulation. Okay, let's go. We got one more again from the same person, Angus Critch. Okay, this is a simulation of a tidal turbine that shows basically the vortex shading that shows the turbulence behind the turbine in real 3D. Again, he's using LES. Okay, you can see over here. So as the blades are rotating, you can see that the wake is generated behind the device. Okay, and the wake or the flow basically the turbulence, it propagates or it persists until several meters, hundreds of meters behind the device. Okay, so this is a very detailed simulation showing the behavior of the flow behind one device. Okay, why this simulation is important? Like wind turbine, when we're dealing with tidal turbine or device, we are not just going to put one or two device at a certain location and then extract energy because it won't be sufficient. We need a few devices or a farm, basically. A farm means a combination of several devices in array where we put and we extract the energy from them. Okay, so now by looking at these two rotors or two blades turbine, we can see that the wake persists up until a certain distance. So now we can understand what is the optimal distance for us to put a device behind the first turbine or the first device. Okay, because if we put the device too close to one another, then the device at the back will extract less energy because remember at the back the wake is still recovering, so the energy, the velocity will be less. So less velocity means less energy can be extracted. Okay, so that's the importance of research like this. Okay, once we understand what is happening, then we can make judgment. Okay, how many turbines do we need? Okay, what are the optimal arrangements that we can use? Okay, otherwise you invest, let's say, 100 million pound, and then suddenly the energy that you extracted from this location is just maybe 100 kilowatt or 200 kilowatt, which is not enough to justify your investment. Okay, so you can see that here the weight generated by the blades as well as the structure. Okay, the structure plays a very important role as well. So you can see over here, for example, are we going to put our device, let's say, right around here? Okay, if we put our device right behind the turbine here, then the velocity is still recovering. So we are not going to get optimal energy extraction. Okay, so maybe we have to put our device somewhere on the side here. It's called staggered arrangement. Okay, so this is the importance of research like this. Okay, right. So I think they are just showing. Okay, so I'm going to stop now. All right. So let's go back. Okay. All right. So just now, before we watch the video, we discussed about computational resource here, computational cost. Okay. Now, how long does it take to simulate something like what we just watched just now? Okay, the research done by Angus Critch. Okay, so I had the chance to talk with him. He showed me his results, and we discussed basically first how it was done, and second, how long does it take? Okay, so for the simulation, for his simulation on the Isle of Islay, where the hydrogen, where he's trying to investigate the hydrodynamics behavior between the two coastline. Okay, if you remember the first video that we watched, okay, that it was done by using fluidity Okay, this is a software, open source. Okay, so open source software. Okay, open source software named Fluidity. That simulation took him 30 days to complete by using supercomputer. Okay, he used LES method. Okay, so just to give you perspective, to get some result like that, just a short amount. I think that the first video was not even 2 minutes. Okay, to get a 2 minutes data or output, okay, as accurate as that using LES method, it took him 30 days to simulate by using supercomputer. Okay, so just imagine how long does it take if you want to simulate a jet, for example, NASA, for example, if they want to investigate the aerodynamics of their spaceship. So just imagine the computational cost involved in this type of simulations. Okay. Okay. So now it goes back to the discussion that we had about LES, DNS. Okay, so now we can see that LES is quite powerful. Okay, we understand now DNS, even though it is accurate, it can solve all the vortex structures, but it can only be used for simple problem. Okay, because it will take too much computational cost. Okay, it's very, very detailed, and sometimes we don't even need all the details. Okay, so LES is a compromise. It solves most of the structures. Okay, and the smallest one is they use subgrid resolution and use a bit of thermodynamics modeling. Okay, so does it mean that the best option for us is LES and DNS? I think one of the students already asked this during presentation previously. It depends on the problem. Okay, if what we want is like Dr. Angus Critch, he's trying to investigate several things. First, the behavior of the wake, okay, or the flow behind the device. Okay, as the flow passing through the device, the tidal turbine, what is the behavior of the turbulence? So that's one thing. If you want something that detailed, yes, we have to use LES. Okay, DNS here in Dr. Angus Critch case is out of question because it's almost impossible. Just imagine supercomputer using LES. It took him 30 days. That's assuming there is no problem in terms of there is no error or bugs in his simulation, in his coding. Okay, DNS, we don't need that detail. Okay, unless we are dealing with something, for example, maybe NASA needs to do something very detailed, then they use DNS. Okay, but it doesn't mean our runs is not useful. Okay, so I'll give you one simple example. So this is the my research for my PhD. I use open source software. I mentioned this before. I use Telemech. Okay, and Telemech basically use runs. Okay, so now why I use a software that basically utilize runs method instead of LES? Okay, in my case, I just want to investigate. Basically, if I put tidal turbine at a certain location, what will be the impact, the wake flow? Okay, how far will the wake travel? Okay, will it impact or alter the environment in the nearby region? Okay, so I'm not interested in looking at the detail of what is happening at that particular specific site. No. Okay, so for example, okay, I've shown you this before in the lecture. This is my domain in 2D. Okay, so my location here is zoom in part B here. Okay, so C here. Okay, this is where I put my device, and this is a mix of structured and unstructured grid. You can see over here. Okay, this is my result on the right side. Okay, now just remember this is the island, the small island here. Here, you can see that if I use 21 device, okay, the wake will propagate or will go up until kilometers, okay, behind the site or the farm. Okay, and if I zoom in, you can see that the velocity deficit. Okay, in this case, I arrange my device to be staggered so that basically no device is directly behind the first device. Okay, and when you see it here, the flow, okay, the wake of the generated from the device is not symmetry. Okay, why is not symmetry? Because this uses the real tidal data. And if you can see here, the shape of the coastline basically it resembles something like this. So meaning that um, the flow coming from the left side of the domain, and then it travels through past this channel, and then it passes through the right side. Okay, basically there's a kind of like a lane. Okay, so it's not a straight line. So that's why you see the wake basically it goes in this direction. So that's one way for you to check whether your simulation is correct because it's replicating the right physics. Okay, so similarly, this is the detailed view, okay, of the device. Okay, so depends on what you are trying to do. For most cases, runs should be sufficient. Okay, unless you are dealing with very something that is very specific, you want to check the turbulence shape of a certain thing, then you go for LES. Okay. Okay. Similarly, this is from my FYP work from my students. You can see that okay, the influence of arrangement. Okay, if we use two devices and three devices, okay, for example, if you put this device at a certain location, okay, you can see that the wake interacts, so it will impact the uh, output generated or output energy extracted by this device, the third device. Okay, so in this case, runs should be suffice instead of LES. Okay, because we are not interested to see what is happening behind in detail. We just want to see the interaction of the wake. Okay, so it depends on the applications. Okay, but there are some drawbacks as for using runs. Okay, because if you remember, runs they cannot solve the smallest structure. Okay, it has to be modeled. So if you notice here, okay, I zoom in over here. Just 1 second, guys. Okay. Okay, so we were talking about the drawbacks of runs. Okay. If you just want to see the general behavior of the flow, yes, runs is okay. But in this case, remember, because runs cannot solve the small scale or the small structure of the vortices, so it's not useful if we want to look at this part. Let's see what color came back. Remember the definition of near wake just now that we discussed. So in the near wake, okay, this is the region where the mixing happens the most. Okay, so because the mixing happens the most, it has a combination of large, small, and medium scale structures. Okay, and because runs take the average value, so the structures or the behavior of the fluids in this region cannot be replicated accurately. So near wake region basically cannot be used for analysis by using runs. So that's one of the limitations. So we have to understand the pros and cons of each methods before we proceed. Okay, all right. So we talk about runs. Basically, it's about the fluctuation combination of the mean value plus fluctuation of the velocity component. Okay. Into details. Okay. Several modeling models available for runs. Okay. In ANSYS, for example, we have Smalat Almaraz, but that's one equation models. Okay, so basically, one equation model is something that we try to avoid if possible. 10 years ago, 15 years ago, maybe people still use one equation models, okay, because the computational resources. It's a good compromise, yes, it's quite okay, but most people use them back in the days because of the limitation of the computational resources. But right now, even on laptop, for high performance laptop, gaming laptop, for example, you can have RAM up until 32 gigabyte of RAM, not storage, for RAM, just for RAM. And then you have SSD for storage. So you have basically more resources to calculate, to do the computation. So that's why nowadays, most simulation uses the two equation models. Okay, for runs, two equation models basically are more accurate. It can give a better simulation values or the values that we want. Okay, so the most commonly used one, as you know, is K epsilon. Okay, so all these K epsilon, K omega, as I mentioned, okay, before you use it, for example, for whatever reason, say let's say you have K epsilon, you have K omega, you need to understand the positive and negative. Okay, what I mean by positive, negative here is basically the strength and the weaknesses of each equations. Okay, so for example, when we are dealing with, for example here, free shear layer flows, external flows, small pressure gradients, meaning that general problems, yes, you use K epsilon. But when you are dealing with near wall behavior, meaning that when, okay, from side view, let's say this is your object. So instead of in the middle of the domain, you have your object located at the bottom of the domain. So that's where you are dealing with the near wall problems. So for near wall, K omega is better because it solves the wall here. This is the small fluctuation here. Okay, so it solves better fluctuations near the wall. So you have to understand the pro and cons of each of these models before you use them. Okay. Okay. All right. So to wrap up, basically, okay, you can see here for one equation models. This is what is available in ANSYS, by the way. Okay, one equation models for me is something that you can just ignore. Okay, for now, because I think most of the hardware right now should be able to run the two equation models. Okay, so for two equation models, okay, these are runs-based model. Okay, you have standard K epsilon, RNG realizable, standard K omega, SST omega, and Reynolds stress model. Okay, again, as I said, please make sure you understand the strength and the weaknesses of each turbulence closure model, the TCM. Okay, the turbulence model is also called turbulence closure model. Okay, so you need to understand all of them. Okay, and then okay, make some remarks over here. These are all available in Fluency FX or Star CD is one of the commercial software. I use this software once, but it's very it's not user friendly enough to say. Okay, so for ANSYS students, we also have options to use LES in ANSYS. Okay, so which is interesting. So if you are dealing with something that requires detailed flow characterization, then we can try to use LES in ANSYS. Okay, and of course, the last one is DNS. So you can see the arrow here. As we go down, as we go to the DNS, as we go closer to that, we increase the computational cost per iteration. Okay, and remember, what does it mean by computational cost? Is about how much uh, kind of energy lah, how much energy is being used, or how much processing power is expected from the computer. This is per iteration. Just remember. Remember for ANSYS, when you did your lab and case study, you have all these K, epsilon, all these U, V, Z, the velocity components, and then you have this iteration. Okay, and this is from your what plot is this? Residual plot, yes, residual plots. Okay, so this is per iteration. Remember when you said, let's say 10 iteration or 100 iteration or even 1000 iterations. So per iteration, okay, the cost involved that we're talking about is per iteration. So just imagine if you have 1000 iterations, okay, and you are using DNS. So just imagine the resources that it needs. Okay. Okay. So just again a bit turbulence modeling. What does it mean again? If we have no obstacles, okay, assuming we are dealing with smooth surfaces, this is what we expect our velocity profile, flow velocity profile to look like. Okay, it's just uniform in all direction. But we understand when we have a wall, okay, a bottom wall here. So at the bottom, the energy here, okay, becomes smaller because remember, because of the friction. So the mixing that is happening at the bottom of the wall. So the largest energy here, okay, and then as it goes down, okay, it becomes smaller and smaller here. Okay, so large eddy scales, we have small eddy scales at the bottom. Okay, injection of energy, remember Kolmogorov, we have production or injection of energy, the energy is largest, and then flux of energy means that the transfer of energy. Okay, the dissipation of energy due to the heat, it converted from the mixing basically generate heats, so it loses the energy, so change one form to another form. So if we use DNS method, it will resolve all the scales, okay, from the large until small. Okay, for LES, most of the scales, but the smallest one at the bottom is modeled. France, it's modeled from the largest until the smallest. Okay, so I think this is a very good explanation in terms of turbulence modeling. Okay, what does it mean by turbulence modeling? Okay, so as you can see over here, some difference in terms of DNS, LES, and RAS. This is the same simulation but using different method. You can see that when you're using runs, the value is uniform, okay, as expected. Okay, using LES, we can see some fluctuation. Okay, but actually in the fluctuation, there is more detailed behavior, like the one shown here, DNS. Okay, all right. So again, as we go from runs to DNS at the top, we increase the computational cost. Okay, and then we get detailed output, of course, but we have the drawbacks, as mentioned. The resources needed is large. Okay, all right. Okay. Okay. So similarly, this is what we looked before. It's quite similar. Okay. So basically, what is important about this diagram, basically what we are not discussing in this course is, apart from the turbulence model, we also have another one that is called wall function. Okay, basically, instead of, okay, as you understand, when we try to resolve the small scale, okay, we need our mesh or elements to be small as well, so that we can capture what is happening at that particular location. But sometimes using too small elements are not, it's not preferable, but it's not possible. So there is another method that is called wall function, Y plus. Okay, that can be used to, or that can be introduced to substitute for the turbulence model. Okay, so this is not part of our course, but I just throwing out the idea so that you can understand there are several methods basically to replicate the behavior of the small vortices or small structures, eddies. Okay. Okay. Okay, so that's why we call it a small wall function. Okay, so again, this diagram is quite interesting. Runs, basically mean flow. LES, large scale. Okay, DNS, all turbulence. Okay, all right. And this diagram is also interesting to make us understand, okay, what is different in terms of the calculation. Okay, let's say we are trying to get the temperature as the variable. Okay, over time. Of course, when you do iteration, it is over time in your simulation. Okay, now let's look at the first one, runs. DNS. Okay, when we look at DNS, let's say blue color here. Okay, all this. Okay, this is DNS, the blue one. Okay, you can see over here. So DNS will try to resolve the variables, okay, at each time or at each t, okay, as it is. Okay, at each location, they will try to resolve it, okay, one by one at each location. Okay, LES, okay, it cannot resolve all the details, okay, most of the details. So you can see that it still follows the line for LES. Okay, it still follows the trend, but not quite as accurate. It didn't capture, it cannot capture the fluctuation. Okay, runs, on the other hand, is the simplest. Instead of worrying about the fluctuation, instead of following the trend, it's just a straight line. They take the value of the average. Okay, so that's what it meant just now for runs, for U runs. Basically, it's just U mean plus U fluctuation. Okay, mean, this is the mean. Fluctuation is what is the value, for example, over here. The fluctuation is the difference between mean and the exact value, in this case here, DNS. So that's what runs refers to. Okay. Okay, again, similar. This is what we discussed about runs. Okay. Okay, again, this is very, very useful for us to understand. We looked at this before. If you are dealing with DNS, everything from the large scale eddies into the small scale is being resolved. For LES, most of them, okay, but for runs, okay, it can only resolve or solve for the large scale eddies, injection of eddies. Okay. All right, so we discussed about this. Okay. Okay, just to show you the influence of turbulence model when you choose in ANSYS, for example. You can see here. Oops, sorry, it's not clear. Okay, you can see here. This is the same simulation but using a different turbulence model. It gives a different output for your simulation. That's why it's important to understand what is the problem that you're trying to solve and choose the most suitable turbulence model, okay, for your problem. You can see that the wake here, the wake length, they are different. That's one thing. And you can see that the properties within the flow, they are different for all models. So that's why it's important to understand. Okay, it's not just okay, use K epsilon for everything. No. Okay, similarly, okay, this shows the difference between runs, LES, and experiment. Okay, experiment, of course, we can see the exact behavior. Runs, this is the general shape, but you can see what is happening basically. Okay, so just to give you some perspective. Okay, I think that's all I have for turbulence model. Okay, before we end our session, just one last thing. Okay, all right, so just to wrap up our discussion on turbulence model. Okay, so have we covered everything in CFD? When we first started the semester, we look at the CFD procedures. We look at the ANSYS procedures in general, about the meshing, about the domain, and then we move to finite difference model, and then we move a bit into finite volume model, and then turbulence right now. So that's basically just a drop in the ocean about CFD. We have so many things that we are yet to touch in CFD. Okay, so some of the topics that we haven't touched, for example, that I put over here. Okay, even this list are not comprehensive. So this is just some of the topics related to CFD that is quite important but not covered as part of our syllabus. Okay, not part of our syllabus. Okay, for example, hydrostatic versus non-hydrostatic. What is hydrostatic? Okay, about grid generation, we did not really go into details. Okay, what is implicit, explicit scheme, um, open source. What is about open source? Okay, so we did not go into details on that. Okay, so I shared this before, and I've shared my experience while using open source software. So this is what I want. Okay, when I first start my study, of course, I have no idea my output will look like this. I think that's similar to your FIP. When you first started your FIP, you know what you want to do, but you have no idea how your report or your output will look like at the end. I assume that's the case. Okay, so this is what I want, but of course, I have no idea this will be the output after several years of study. Okay, so along the way to get this, okay, I have to write a code. Okay, I have to modify subroutine. So I've shared this last week. Open source is quite powerful because you can modify the behavior of the flow as you please or as you want. But because it's open source, it's free. So mostly you need to do some modification by yourself. Okay, you need to do some editing. Okay, basically you need to come up with something. It's not just basically just using click one button and then you get the result. Okay, I showed you basically to get this, I have to make some adjustment on the subroutine. And of course, this is not just about the output that I want. It's about the journey, basically, how I get from knowing nothing about the hydrodynamics of the ocean into producing something like this. Okay, so I think that concludes our lecture for this semester. So we covered basic philosophy or introduction to CFD at the start of the semester. And then instead of the second one, I think we go into the hands-on detailed applications. We covered the theory, which is CFD procedures, and then also we look into the use of NC software during the lab. And then after that, so this is our second one, first one. And then we look at, for the third one, is the fluid flow equations, which is the partial differential equations of fluid flow. This is a recap from your fluid dynamics course. We look at how we derive the Euler and also for the Navier-Stokes equations. And we look at the importance, basically, you need to understand, okay, how we get to the Euler and Navier-Stokes equations, not just, okay, that's the end or the end product equations of Euler and Navier-Stokes. We need to understand how to come up with that, to how the equations are generated, so that we can get the fundamentals behind the equations. Okay, how tau, the sigma, the pressure, the gravity, we need to understand all that. Then we move into the discretization method. Remember, in the software, you try to replicate what is the physical problem. Okay, but you have to make some simplification or assumptions. Okay, and their assumptions from physical phenomena. So instead of looking at the details mathematics, we now look into something that is being simplified. Okay, the function is now being converted into algebraic equations, something that is easier for us to solve. So discretization method, basically you move from one function into algebraic equations, so that is easier for you for the software to solve. And in this case, we look into finite difference model and also a bit on the finite volume. Okay. All right. I think that's all I have for today and for the semester, I guess. All right. I know it's already 5 o'clock. I'm going to stop now. Okay. So I'm going to pause, maybe stop.